So in this review video, we're going to be going over the concerted and sequential models. That is what the vast majority of you all reported as being most confusing in your reflections, and so I think it would be time well spent to just talk about these two models once again a little bit more slowly and deliberately than I did in the lecture, just to get a handle on how they work. So just like we started in the lecture talking about the concerted model, we will go ahead and start talking about that same model here. And so let's start off by saying that we have some enzyme in the R form, and we're going to make this a trimer, which means we have 3 subunits, and we have some enzyme in the T form. And it doesn't matter how the subunits are configured, it's the same enzyme, it's in the same configuration. And they are in an equilibrium, but that equilibrium favors the T form much more than the R form. So let's say, for argument's sake, that at any given time, this is a 90-10 split or proportion. In other words, 90% of the enzyme remains in the T form and 10% remains in the R form. So the enzyme excuse me, is heavily tilted in favor of the T form, but there is some free R form enzyme around. And I should have defined it a little bit earlier, but hopefully you remember that T stands for tense or taut, and what's tense about this is the substrate binding site, the active site, and so T form does a very bad job of binding to substrate. R stands for relaxed. What's relaxed is the configuration of the enzyme, and what that relaxation allows is for good substrate binding to the active site. And just to put a finer point on it, we're talking about 2 different conformations of the same enzyme. That means we're talking about an enzyme that can take on 2 different shapes, an R shape and a T shape, and any enzyme that changes its shape is an allosteric enzyme. So what we are talking about here is a model for allosteric enzyme behavior. Alright, so let's say we go ahead and start this, and we're starting with a total of 100 molecules, 100 enzymes. And if we have 100 enzymes total, that means 90 of those enzymes are in the T form and 10 of those enzymes are in the R form. We always have to maintain this 90-10 ratio. That is the equilibrium ratio. That's when the levels of these 2 conformations are thermodynamically balanced. So a 90-10 split, 90% in the T form, 10% in the R form, that's 90 in the T and 10 in the R for a total of 100. And let's go ahead and add substrate to this reaction. So we'll add substrate, I guess we'll make substrate purple. So substrate binds, substrate is added, right? And that substrate is going to bind to the R form. It's the only form it can bind to. So substrate binds to the R form, and it binds to all of the R form it can find, and as soon as we have enzyme substrate complex is a completely different thing than free enzyme. They are not one and the same. So now, once we have this substrate bound to the enzyme in the R form, we have no more free R form enzyme. We're down to none. It's all bound by substrate. So what that means is we now have a total of 90 enzymes to work with, because the other 10 enzymes are something different. They're enzyme substrate complex now. If we have 90 enzymes to work with, and we have to maintain this 90-10 ratio, then what that really means is that 10% of that 90 has to go forward and become R form. So let's shift some of these to the R form. Now we don't have to be so vague as to say some, because we know exactly how many we need to shift. We have to shift 10% of our total. 10% of our total is 9. So now we have 9 in the R form, and if we have 9 in the R form, that means we've cut down our pool of T form to 81. But remember, there's substrate around. So what is that substrate going to bind to? It's going to bind to the R form, the only thing it can bind to. And when substrate binds to the R form, we just created enzyme substrate complex, which is a completely new thing. And so this isn't free R form anymore. Enzyme substrate complex floats off and goes somewhere else. But now we're out of balance. We have 81 T form and no R form, and we have to maintain that split. So we have to shift 10% of our T form into the R form. And we don't have to say some, because we know that about 10% of 81, roughly speaking, is 8. And if we have 8 in the R form, we cut this pool down to 73. This is what I meant in the lecture about shifting the equilibrium. We're moving T form into R form because every time R form binds to substrate, and every time we make more enzyme-substrate complex, we're essentially taking that enzyme-bound R form out of the equation, and in order to maintain the 90-10 balance that we have dictated, we have to continue shifting T form into R form. That would be about 7, and if we drop this by 7, we would be to 66, I believe. 64, I'm sorry. So we can continue to shift the equilibrium to the R form by continuing to bind that R form to substrate. When all of that substrate goes to product, what's going to happen? Well, we go to product. That means we have free enzyme. All of that enzyme builds up in the R form because that's the state it was in before. But now we've got all this R form enzyme around. Back to our 100. Now we've got 36 R form and 64 T form, and that's not in balance either. And so the equilibrium in this point is going to shift to the right, back to the T form, because we have to maintain that balance. If we have a total of 100 enzymes, we will always seek the balance of 90%, 10%. And so all that freed enzyme that was in R form will spontaneously spring and shift back to the T form. So that's the concerted model. The reason why it's the concerted model is because never did we see hybrid enzymes where T and R form were mixed by subunit in a single enzyme. This is concerted. All of the subunits shift simultaneously. Entire enzymes go from T to R, and the direction they shift in, from T to R or from R to T, depends on maintaining that equilibrium balance. We can contrast that to the sequential model. We can start the model the same way, except for the sequential model, all we have is enzyme in the T form. The sequential model states that there is never free R form enzyme around at all. And so some substrate builds up in the cell, but T form doesn't like to bind substrate, so nothing really happens. And more substrate builds in the cell. T form doesn't like to bind substrate, so nothing really happens. And more substrate builds up in the cell, and more, and more, and more. And now we get to such high substrate concentrations that the substrate has to go somewhere just to get away from that large amount of concentration. And where it goes is it'll forcibly, finally, squeeze itself into a T site, because there's nowhere else for it to go. So even though it's a poor fit, it's a fit enough that at high substrate concentrations will bind. And there's no way that an active site can stay in the T form when it's bound by substrate. So that T form spontaneously shifts to the R. So now we have a mixed enzyme that has one subunit in the R form and other subunits in the T. That conversion into the R form created a wave of movement in the enzyme. And that movement propagates. So because the enzyme is shifting in order to accommodate that R form transition, this neighboring subunit does a bit of shifting as well, and it will then turn to the R form. Well, as soon as it's in R form, what of course is going to happen? This substrate is going to love that R form, and it binds there. And that induces a wave of motion that propagates to the rest of the enzyme and shifts it to the R form. And so now we have the sequential progression of an enzyme from the T form to the R form. One subunit switched because it had to accommodate substrate binding, and then the subsequent subunit shifted to R form as a result of the conformational change of the first subunit shifting. One primary difference between the sequential and concerted models is that in the concerted model, you have the R form free, and then substrate binds to it. In the sequential model, there is never free R form. Substrate binds first to T form enzymes, and that induces the shift to the R form. In the concerted model, the entire enzyme shifts from T to R at once. In the sequential model, because the next shift is always depending on the previous binding, we have the shift of subunits from T to R one at a time. First one subunit, then the next, and finally the next. One more point to make before we wrap this up. Back to our sigmoidal plots. This is the plot of any generic allosteric enzyme, and it's sigmoidal because it shows positive cooperativity. But now that we've seen the entire lecture, and we've talked about sequential and concerted, let's look at this one more way. We see in this plot that the activity starts very weak or slow, the enzyme activity. So at low substrate concentrations, we have low velocities. The enzyme doesn't work so well. But then we reach some kind of critical substrate concentration, after which we get a much faster, more efficient, stronger response from the enzyme. The enzyme works much better. And this is the definition of positive cooperativity that we talked about in lecture. It starts very hard and it gets easier, like rolling a car. But now that we've talked about the sequential and concerted models, what we actually see is that the reason why things are so weak and slow and hard in the beginning is because enzymes are in T form, primarily. And what gets the reaction moving much faster later on is that the levels of R form enzymes are increasing. If we were talking about the concerted model, what's happening here in these early stages is we have a small amount of R form enzyme that is binding substrate, and these are the early stages of shifting the equilibrium to the R form. As more and more enzyme is shifted to the R form and more enzyme is in the R form, all those R form enzymes are working faster together, and we get more activity. We can also explain this trend by considering the sequential model. What's happening at these low concentrations in the sequential model is that those substrate concentrations just simply aren't high enough to squeeze themselves into the tight active site. This critical amount of substrate here is the point at which enough substrate is possible that we get that forced binding of substrate into the T site, and that shifts it to R. Once we have one shift to R, what happens next? Other subunits shift to R, and because other subunits are shifting to R, we bind substrate more easily, which allows us to have a faster, more robust reaction. The reason why the sequential and concerted models are both correct and both applicable is because both of them explain the sigmoidal positive cooperativity of allosteric enzymes. And some enzymes functionally, mechanistically work as concerted enzymes and others work as sequential. So we've got a lot that kind of comes together at the end of this lecture that we don't have really the opportunity to explore in class. And what's coming together is how the T and R forms explain, respectively, the difficulty and ease of an enzymatic reaction progressing. With most enzymes in the T form at early substrate concentrations, that reaction is a very hard one to start. With more and more R form enzymes at higher substrate concentrations, we see a faster and faster reaction at those substrate concentrations. So hopefully this does a better job of not only clarifying concerted and sequential enzymes, but hopefully it serves to tie together some of the seemingly separate and disparate concepts that really do come together at the end of this lecture.